So, as Professor João Praça said, my internship was in Explainable AI for real-time defect prediction and prescription in a production line. So, first of all, I'm going to explain a bit what is Explainable AI, so that for those of you who don't know. So, Explainable AI is the process that allows human users to understand and comprehend the output of a machine learning model. So we are able to understand an output given a specific input, and we are able to link them together. This has three main advantages. So it gives us the opportunity to improve our analysis of the model and the data. It makes it easier to explain to people who are not familiar with ML models how the model makes decisions. And it can also help us avoid negative and unforeseen consequences of this particular model. So these three factors of explainable AI give us more confidence in our model and therefore increase its trustworthiness. So there are some simple machine learning models such as linear regression and decision trees, which are easier to understand and to explain. And therefore they are called white box models. So we can, in these kind of models, we can easily establish a relationship between the data used to train the model and the model output. So then we can explain it, why the output was given, why a certain outcome was given a specific input. However, there are more complex models, such as deep neural networks, which, although they can be much more accurate, they are much more difficult to understand and to explain, and so they're called black box models. The main challenge of explainable AI is basically to understand this kind of complex models much more easily, and consequently increase our trust in them so that we can understand why the decisions are made based on the input data. So currently there are mainly two algorithms in explainable AI that generally produce good results, whether independently of the model we use and the data set. So those are LIME and Shap, and first of all, I'm going to talk about LIME. So LIME stands for Local Interpretable Model Agnostic Explanations, and as the name says, it supports explaining individual predictions, so a single sample, by approximating a complex model to a linear model in a specific region around the vicinity of a particular instance. So for example, in this image, we can see a complex function on the left, and the white background means there is a stroke, and the blue background means there is no stroke. And if we zoom in on a specific region, for example, in this where this pink dot is, we can approximate this region of the model to a linear model so that it is easier to understand, and we can clearly state that the pink dot is in above the line, the linear line, so we can say that it means there is a stroke. And next, there is Shap, which means Shapley additive explanations. And as the name says, it uses Shapley values to create an explanation. So what are Shapley values? Shapley values are calculated to get the contribution or impact of a feature in a model. So features such as age or gender. So what it does, it compares how the model behaves with and without those features. So for example, it tests how the model behaves with age and with all the other features, and how the model behaves with all the other features except age, for example. However, features can also interact and work together. So, for example, two features only obtain good results if they work together and not individually. So to get the full contribution value of a specific feature, we need to calculate its contribution with every subset of features. At the moment, there are two well-known Shap implementations. So there is Shap, which is basically what I just explained. And there is also kernel Shap, which is kind of a mix between Lime and using Shapley values. The kernel Shap usually tends to be more accurate, but it also takes much more time to execute. And Shap also obtains fairly good results. So in the context of my internship, we needed to figure out in real time what were the features that contributed the most for a defect in a wood plate production line. So we've tested these three algorithms on an XGB boost model with the data of the production line and got the top 5 features that contributed to the most for the model output. Overall, all the algorithms presented similar and apparently good results and considered features most important, such as the length of the wood plate and time interval between production of 2 pieces. However, kernel Shap took a very long time to process an explanation. So, and as our goal was to give an explanation in real time, we put kernel Shap aside. And between Shap and Lime, both of them gave good results and were fast. And Lime will run in about under a minute, but Shap gave us an explanation basically instantaneously. So it was considered the best explainable algorithm for this particular case. Next, there was the optimization part of the internship. So what we had to do was to apply these concepts on a wood plate production line, as I said. And in this production line, some units were defective, and our goal was to understand why they were defective, what was causing that defect, and what was the best way to avoid it. And the main challenge of this internship was to create a new algorithm that optimizes the defect samples, that is the features of the samples, and gives us a prescription so that the outcome would change from non-defective to or from defective to non-defective. So basically, analyze a specific sample and adjust some values and give us those values so that we can change those values in a machine, and hopefully the number of defects reduces. However, there was one big conditioning, that was only 5 of all the 30 features in the samples could be modified in real time. So we were very restricted on what features we could change. And furthermore, these features, the values cannot be changed drastically. So as it would either be physically impossible or they cannot be changed that much in a small amount of time. So we had to create some boundaries and apply them. So there was already a version of this optimizer developed by Artur Freitas from the lab. And the main issue there was, and that we had to solve, was that with the samples that have above 99% chance of being defective. So in these cases, the optimizer could only reduce the percentage of defect from above 99% to about 80 to 90%. And our goal was to get it below 50%, so they could be considered non-defective. So, and also to prevent the optimizer to getting stuck in a potential local minimum, we decided to apply a new strategy. So instead of optimizing all these 5 features that we could change, firstly, we would get the 2 most contributive features from those 5 using the Shapley values given by the tree Shap. And then we would optimize only those 2 features and save them in a new sample. And then we would optimize this new sample given now that it is in a new optimized starting point. So hopefully we could escape from this local minimum to a global minimum, and the defect would be much more reduced. So as I said, we applied this strategy using 2 local optimization algorithms. We used Powell and Neldermead. But as you can see in this table, comparing the rows from the 5 features and 5 optimized with Powell and Neldermead, the results are the same. So this strategy did not alter any metrics at all, either the average, standard deviation, or the number of, or the percentage of defective, non-defective samples. So this occurred either because there was no local minimum, or it was not, this strategy was not enough to escape from it. So after this, we decided to use 2 global optimization algorithms, dual annealing and Bayesian hopping, so that we can hopefully escape from this local minimum. So dual annealing, as you can see, did not improve the results. It was basically the same as the local algorithms, but Bayesian hopping did in fact improve the results in a significant way. So the average was, for example, around 77, and it reduced to 54%. So, however, we suspected these results. They were a bit too good to be true, let's say, and we inspected them a bit further and realized that the boundaries weren't that we had established weren't being fulfilled. So what we decided to do next was to apply these boundaries in a new cost function in the Bayesian hopping algorithm. So the farther a sample is away from the boundaries, the much higher it is the cost function result, that is. However, in this case, the results were not satisfactory at all. In fact, it was the worst of them all, even the ones from the local optimization. So this is basically what I did in my internship, but there are some next steps that I've already started taking but haven't finished yet. So we can ease a bit of the boundaries by a small percentage, so that we can maybe reduce the percentage of defect a little bit. We could also plot the neighborhood of the worst samples to check for a local minimum. That is, we could select the worst samples, like the 5 worst samples, and generate the neighborhood around it, and calculate the cost function for those in this neighborhood, and then plot it and see how it behaves in the vicinity of the sample, to check if there is a local minimum, or if there is no local minimum and is no further improvable, let's say. And after this analysis, we could then improve the Bayesian hopping cost function. So we maybe could change a bit the weights, reduce a bit of the weights, or improve the weights of the boundaries, and also add the score cost, like the result being the percentage, that is, of the defect being instead of 99%, it would be reduced. So higher the percentage, the worst. And basically that is it. I'd like to say thank you for your attention, and thank you to João Reis and Artur Freitas especially for guiding me and helping me throughout this internship. And that's it. Now I'm open to your questions if you have them.